All right, so lesson 5, refraction through lenses. So if you wear glasses, your glasses have lenses in them. The lenses help bend the light so that when it enters your eye, it actually hits your retina in the right place and you see images more clearly. So, types of lenses. So when light passes through a lens, there are two refractions. One when the light ray enters the lens, so for example, right there, and one when it exits the lens, so here. And there are two types of lenses that we study in Physics 30. The first one is called a converging lens. Notice that for a converging lens, the sides of the lens kind of bulge out. And the reason it's called a converging lens is that the light rays all converge or come together at one point there. And converging lenses are sort of like concave mirrors in the sense that they mostly produce real images. There's one case where they produce virtual images, but most of the time, real images. Okay, and the other type of lens we study is called a diverging lens. The difference with this one is that the sides of the lens are not bulging out, they're actually going inwards. But again, there's two refractions, so there's one refraction when the light enters and another refraction when the light exits the lens. And then this one's called a diverging lens because when the light comes out of the lens, it's getting further apart over here. And diverging lenses are like convex mirrors in the sense that they only produce virtual images. So I kind of said this already, but converging lenses are like concave mirrors and diverging lenses are like convex mirrors. So remember how for mirrors, we had the three special rays that we would use to draw ray diagrams. We can actually use the same special rays for drawing ray diagrams for lenses. So here's what the special rays look like. So for a converging lens, here's ray number 1. Okay, so we have our lens in the middle. We still have our principal axis. We still have a focal point. The difference here, though, is that you can write the focal point on both sides of the lens. So because the lens itself is symmetrical, you could write the focal point on either side like this. Also, this is our center of curvature here, which sometimes you'll see that referred to as 2F instead of C, because remember the center of curvature is going to be twice as far from the mirror or the lens as the focal point is. So sometimes 2F instead. So we have our incident ray. So the incident ray is coming from the tip of the object and it's traveling towards the lens. And then that ray is going to pass through the lens. It's going to refract, and we draw the refracted ray as a dotted line. And so here's special ray number 2 for a converging lens. And here's special ray number 3. The difference with special ray number 3 for a lens as compared to a mirror is that special ray 3 for lenses does not pass through the center of curvature. Instead, it just passes through the very middle of the lens right there. Okay, so image formation example. So let's say we have an object, okay, and we draw all 3 special rays at the same time. So I've gone ahead and done that. Just like for mirrors, what you do is you look for the place where your dotted lines cross. So for lenses, we can say the image forms wherever the refracted rays meet or cross, and so we can draw our image here. I want you to think about for a second, is this image real or virtual? Well, there's an easy way to tell. We learned when we were studying mirrors that real images are always inverted and virtual images are always upright. So when we look at the arrow here for the image, that arrow is upside down. So this has to be a real image. Okay, we can also draw our special rays for diverging lenses. So there's special ray number 1, special ray number 2, and special ray number 3. Okay, and so if we're drawing ray diagrams for lenses, just like for spherical mirrors, there's 5 cases to consider if you're working with a converging lens. For diverging lenses, there's only 1 case to consider. So here's case 1 for a converging lens. So we see here that our image is smaller, inverted, and real. For case 2, no change in size, inverted and real. Case 3, the image is bigger, inverted and real. Case 4, no image forms. And case 5, so here I've drawn this twice. The first one, I'm just drawing the 3 rays. So I'm drawing my 3 special rays, but I'm not drawing my object. And then in the second diagram, I've actually taken my dotted lines and traced them back. And they all meet right here. So that's where my image forms. Okay, so we can see here the image is larger and upright. And it's also virtual because remember, whenever you have to trace anything, like you have to trace your dotted lines back, that's going to give you a virtual image. And then for diverging lenses, there's just the one case. So I kind of did the same thing again. First, I just drew the 3 special rays. And then in the next diagram, I traced back the refracted rays. And also, just because this diagram was getting really messy, I erased the incident rays just to make it easier to see. So here you can see that your your image is smaller, upright, and again, because we trace things back, virtual. So in your notes, I've just put all of these in there so that you can look at them all in one page. Okay, so whenever you're working with lenses, the front of the lens is always the side that the object is on. So here, I just wanted you to label, okay, wherever the object is, that's the front. And whichever side is not the front of the lens would be called the back side of the lens. Okay, just be a little bit careful. So mirrors and lenses, I should say, kind of do 2 opposite things. So while real images form in front of a mirror, real images form behind a lens. And that's because the mirror and the lens are acting in opposite ways. So while mirrors reflect light back, lenses refract light through. So just be careful with that. A way to remember this is that real images always form behind the lens, or another way to think about that is if it's a real image, then the object and the image will be on opposite sides of the lens. Okay, whereas virtual images are going to form on the front of the lens, or again, you can remember this by saying, okay, your object, which is right here, and your image form on the same side of the lens if it's virtual. And then I kind of alluded to this earlier in the lesson, but just like for mirrors, okay, virtual images are still upright and real images are inverted. So the only change for lenses and mirrors is really this stuff here from this slide. Everything else is the same for lenses and mirrors. All the sign conventions are the same, the formulas are the same, whether it's, upright or inverted is the same. Okay, so as I just said, the equations for lenses are identical to the equations for mirrors. And here are the sign conventions for lenses. So let's just look at the focal length for a second. Remember that a converging lens is really similar to a convex mirror. So just like convex mirrors have positive focal lengths, converging lenses do too. And for diverging lenses are similar to convex mirrors. So just like convex mirrors have negative focal lengths, so do diverging lenses. And then if you look at the rest of the sign conventions, right, they're identical to the conventions that we learned earlier for mirrors. Okay, so for examples, example 1, a 4 centimeter tall object is placed 50 centimeters away. So let's make our variables list here. So the height of the object is 4 centimeters. It's placed 50 centimeters away from a converging lens that has a focal length of 20 centimeters. Okay, so HO and DO are always positive all the time, so that's fine. But remember, for the focal length, we need to think about whether it's positive or negative. So a converging lens always has a positive focal length, so this is going to be positive 20. And we want to describe the image formed, which means we want to talk about the size, the orientation, and the type of the image. So just like before, to do that, I'm going to calculate DI. So using the focal length formula, I can rearrange for DI. Okay, and so 1 over F, let's go down here, 1 over F, that's going to be 1 over 20 centimeters, minus 1 over DO, so 1 over 50 centimeters, and whatever that is going to be 1 over DI. So I did that earlier, and I got 0.03 centimeters inversed. So that means DI 1 over 0.03 centimeters inversed, which gives 33.3 repeating centimeters. Okay, so when I look at this DI value here, I see that I got a positive value. So because it was a positive value for DI, that tells me that this is a real image. Okay, and we also know that if it's a real image, that it's going to be inverted. Okay, so now let's go ahead and let's calculate the magnification. And we're going to calculate the magnification so that we can actually talk about the size of the object. So magnification, negative DI over DO. Okay, and so negative 33.3 repeat over 50. Centimeters cancel out, leaving us with something that's unitless. This gives negative 0.6. Okay, when we're looking at the magnification, remember we look at the two parts separately. So we look at the sign, and then we look at the number, and we think about what each one of those things tells us. So negative magnification tells us that we have an inverted image, which is good because we already figured out over here that we have an inverted image, and those two things need to match. If they don't, you've done something wrong. And because this number part of the magnification is less than 1, that means that the image is smaller than the original object is. So this would be the smaller, inverted, and real case. And we can verify that, right, by saying, okay, well, if the focal length of the mirror is 20 centimeters, that means the center of curvature is double that, and it's 40 centimeters. And if DO is 50 centimeters, well, 50 is bigger than 40. So we're in the beyond C case, which is case 1. Remember, for case 1, that's the SIR case. Okay, example number 2. So a 50 centimeter tall object is placed 60 centimeters away from a diverging lens. Okay, so again, HO, which we didn't actually end up using for anything in example 1, is 5 centimeters. DO is 60. And both of those are positive, just like always. And this time we have a diverging lens. So we have to remember to make the focal length negative. Other than that, though, it's going to be basically the same process as the last slide. So 1 over F equals 1 over DO plus 1 over DI. So 1 over F minus 1 over DO equals 1 over DI. Okay, so 1 over F, that's 1 over negative 40 minus 1 over DO, so minus 1 over 60. And that gives 1 over DI, which is negative 0.0416 repeat. Since this is 1 over DI, the units are centimeters inversed. So DI is 1 over negative 0.0416 centimeters inversed, which gives negative 24 centimeters. What you should do now is you should pause the video and put this in your calculator just to make sure you're getting the same answer. Because if you don't use brackets properly when you're typing this in, you're not going to get the right answer. Okay, so now we look at DI. We see what the sign of DI tells us. Because DI is negative, this is going to be a virtual image. Okay, and anything virtual is always upright. So there we go. Okay, and then the magnification. So to do the magnification, negative DI over DO. So negative times negative 24 over DO, which is 60. That gives a positive value. Now you don't have to write the plus sign there, but I'm just doing it to be clear. So it gives positive 0.4. So the positive part tells us that it's an upright image. And remember to double check that it matches this, and it does. And then because 0.4 is less than 1, okay, that tells us that our image is smaller than the original object. So we're in the SUV case, smaller upright virtual, which makes sense because for diverging lenses, it's always going to be the SUV case. Okay, so example 3, an object is placed 20 centimeters from an optical device. An upright image of the object is found on the opposite side of the optical device. Okay, let's just worry about dealing with that part first. So it's an upright image. And we know that if it's upright, it must be virtual. Okay, now we know that mirrors form virtual images behind the mirror. Okay, whereas for a lens, because mirrors and lenses do opposite things with light, for a lens, a virtual image forms in front of the mirror. Or in front of the lens, I should have said. So here, when they use the word optical device means it could be a lens or it could be a mirror, and they're not telling you which one. And so you have to figure out, is this a mirror or is this a lens? And because they're telling us that the object is found on the opposite side of the optical device, so what they're saying is the object is on one side and the image is on the other, we're in this case here. It's a mirror, not a lens. And so the reason that I'm going through all of this is later in the question it says, what kind of optical device is it? So we'll need to specify in our answer that it's a mirror. But we'll also need to say what type of mirror, right? So is it concave mirror or convex mirror? So let's worry about whether it's concave or convex after we find the focal length. So it says, what is this mirror's focal length? So writing down numbers, so DO is 20 centimeters, always positive. The image is 1/4 the size of the object. So when you're writing down your magnification, you need to think about both the number and the sign. So because it's an upright image, it's a positive magnification, and it's 1/4 the size, so 0.25. And then we are going to need to find DI so that we can actually put DO and DI into the focal length formula. So let's find the magnification, or let's use the magnification to find DI, rather. Okay, so M is negative DI over DO. So DI is negative M DO. So that's negative times positive 0.25 times DO, which is 20. So DI then is negative 5. Okay, so now let's find our focal length, okay? So 1 over f is 1 over dO plus 1 over di. So we have 1 over 20 plus 1 over -5. And that gives negative 0.15 centimeters to the power of -1. So for our focal length, 1 over negative 0.15 is negative 6.7 after you round centimeters. Okay, so now we are actually good to answer the question. So we found the focal length. That's part of what it asked us for, but it also said what type of mirror it is. We know that convex mirrors have negative focal lengths. So this optical device must have been a convex mirror.